Let's discuss linear systems with 3 variables. The big picture behind systems of 3 variables is that we're going to have 3 equations to work with. And we want to take those 3 equations and turn them into 2 equations and 2 variables. We'll use elimination method to get a system of 2 equations with 2 variables. And then we'll use our techniques for solving 2 equations and 2 variables to find those 2 variables. And then once we find those 2 variables, we can substitute those variables into one of the original equations and solve for the 3rd variable. And then we get a solution for all 3 variables, which will be an ordered triple. Just to compare the 2 scenarios we're looking at, to solve a 2 equation, 2 variable problem, we have an ordered pair that will be our solution, and that ordered pair occurs when the 2 lines intersect. If they don't intersect, we don't have a solution. If they overlap, we have infinitely many solutions, which we've talked about before. But solutions to a 2-variable linear system will be an ordered pair. A solution to a 3-variable linear system is what we call an ordered triple. And we usually represent this by x, y, z. For linear equations with 3 variables, we don't have lines in 3 dimensions, we have planes. And so we see a picture here, we have 3 planes represented by these rectangles. And this dot here, where they come together, where they intersect, gives us our solution, our ordered triple. We could have lots of different scenarios for solutions for 3 equations and 3 variables, and we'll discuss that in just a moment. But let's start out with a simple example. Determine whether this ordered triple is a solution of the system. So we have a system of 3 equations and 3 variables, and we want to know, does that ordered triple solve that system? Just like we did with systems of 2 equations and 2 variables, we're going to take that possible solution and plug it into each of these equations and check to see if it works. So pause your video at this point, try it on your own, and then when you resume, you can check and see if you got the same thing that I did. Plugging in -4, 2, 5 into each one of these 3 equations for x, y, and z, we do get true statements in each of the 3 equations. So this ordered triple is indeed a solution of the system. A linear equation with 3 variables is a flat surface called a plane in 3-dimensional space. When we solve a system of 3 linear equations in 3 variables, there are lots of ways those 3 planes can be oriented in 3D space, since each equation represents a plane. A solution of a system of linear equations in 3 variables is an ordered triple that satisfies all 3 equations and lies on all 3 planes. We've got lots of different pictures. I'll shrink it down so we can see all of them at the same time. For each of these situations below, we want to decide how many possible solutions there are in each of the scenarios. Notice in problem number 1, we have 3 planes, A, B, and C, and they all intersect. The planes are all intersecting on a line. And so we have an entire line of solutions, and just like for systems of 2 equations, we're going to have infinitely many solutions in this case. In the second picture, A, B, and C are not touching at all. Since they're all parallel, there are no intersections. We have no solutions. In the third picture, we see A, B, and C. A and B are intersecting in a line. A and C are intersecting in a line. And C and B are intersecting in a line. But all 3 planes are not intersecting at the same place. We don't have a point where all 3 of those planes are coming together. So even though we have intersections here in number 3, we end up with no solutions because all 3 of the planes are not intersecting at a point. In the fourth picture, all of them are intersecting in that single point right there in the middle. And this system has one solution. In the fifth picture, we have something similar that we have for picture 3. A and B are intersecting, A and C are intersecting, but B and C don't intersect. It looks like they are parallel. And since we don't have one place where all three of them intersect, we have another situation of no solutions. Recall that consistent systems have solutions. Since 1 and 4 have solutions, 1 and 4 are graphs that are representing consistent systems. Which of the graphs represent equations that are dependent? Well, dependent equations are equations that are going to create essentially infinitely many solutions or intersect in infinitely many points. For systems of 2 variables, we saw this when 2 lines were overlapping. They created the same line. In 3 dimensions, dependent equations are planes that'll intersect in a whole line. So 1, 3, and 5 have that situation where the planes are intersecting in lines. So even though we have dependent equations in 1, 3, and 5, only graph 1 has solutions. So this is a very different scenario than our 2 variable systems. In our 2 variable systems, if we had dependent equations, we also had a system that was consistent because we had infinitely many solutions. Those 2 lines were overlapping. But now in 3 dimensions, we have more possibilities. We could have a situation where our equations are dependent, but we don't have solutions at all. Next up, we'll look at how to solve these systems.